Hey everyone, our third mini lecture is going to be about position vectors and force vectors. Now, for our third mini lecture objectives, students will be able to represent a position vector in Cartesian coordinate form from a given geometry and represent a force vector directed along a line. Now, for position vectors, a position vector is defined as a fixed vector that locates a point in space relative to another point. So, consider 2 points, point A and point B, in 3D space. Let their coordinates be xa, ya, za, and xb, yb, zb, respectively. The position vector directed from A to B, or RAB, is defined as RAB XB minus XA in the I direction, YB minus YA in the J direction, and ZB minus ZA in the K direction. Please note that B is the ending point and A is the starting point. So always subtract the tail coordinates from the tip coordinates. And that's how we get our position vector. A force vector directed along a line. As you can see, if a force is directed along this line, then we can represent the force vector in Cartesian coordinates by using the unit vector and the force's magnitude. So we need to first find the position vector RAB for 2 points along that line. Then find the unit vector describing the line's direction, UAB, okay, which is the vector RAB divided by RAB. Multiply the unit vector, okay, UAB, by the magnitude of the force. So we get our F vector along this line is equal to F magnitude times unit vector UAB. That's basically how we get the force vector directed along any line. Let's see an example. So given a 400-pound force along the cable DA, okay, we have this FDA 400-pound magnitude. The force F, we want to find the force FDA in the Cartesian vector form. So our plan is to first find the vector RDA and then get its unit vector UDA. After that, we can obtain the force vector FDA as 400 pounds magnitude times that unit vector UDA. Okay, so the figure shows that when relating D to A, we have to go minus 2 feet in the X direction, or minus 6 feet in the Y direction, and plus 14 feet in the Z direction. So we get our RDA is equal to minus 2I minus 6J plus 14K. We can also find RDA by using the other method, which is subtracting the coordinates of D minus the coordinates of A, which we just saw before. Once we get our RDA, okay, which is minus 2I minus 6J plus 14K, we get the magnitude of RDA, okay, square root of 2 squared plus 6 squared plus 14 squared, and it's equal to 15.36 feet. Then we get our unit vector UDA, which is the vector RDA divided by the magnitude RDA. After that, we get our FDA is 400 times the unit vector of this RDA vector. So FDA is going to be equal to 400 pounds times minus 2I minus 6J plus 14K divided by 15.36. And we get our FDA force along this line, DA is equal to minus 52.1I minus 156J plus 365K. So now that we got our force FDA acting on the crane, we can do the same thing for our force FBA and our force FCA and get the resultant force by adding them all together. Since all of them are in Cartesian form, which is IJK, okay, it will be easy to add them together. And then adding them together, we get a resultant force on the crane, and we can check if the crane will break or not which is going to be your job as future engineers. So that's basically all for today's mini lecture 3. I'll see you guys next time.